So in the first lecture, what we have done is we have had a small round of introduction wherein I have updated the basic terms we would be using in the spherical mirrors. Now let's go a bit ahead and let's talk about focal point or focus. Okay, and let us start with concave mirror. Now let's draw a concave mirror. As I said, it is caving in and it is painted from outside. Okay, now let's draw a principal axis. You know what is principal axis? Principal axis is from the pole to the center of sphere, center of curvature. Now let's say a parallel ray is coming. Now we know that parallel ray it's coming straight towards the mirror. So what we will do is first we will draw, remember, first we will draw the normal. Now the normal always passes, this will be C, will be here. Remember, normal always passes through the center of curvature. So the normal would be something like this. Now what will happen is this angle of incidence would be angle of reflection. So this ray will get diverted and it will go here. Correct? Similarly, if we consider another ray, it will come straight and then we have to draw a normal. Correct? So this ray will get deflected and it will go here. Now the common point where the two rays in such a scenario meets is called focus. Okay? Now whatever I just explained, if I have to write it, then I can say para-axial rays. I will tell you the meaning. Para-axial rays of light coming parallel to principal axis of a concave mirror. So, okay, remember para-axial rays, this means, let me write it with a different pen. This means very close to principal axis. Okay, and if it is very far, it is called marginal rays. Opposite is, I can say, opposite of para-axial is marginal rays. So which means it is bit broadly distributed. Now, so para-axial rays of light coming parallel to principal axis of a concave mirror after reflection meet at a common point on the principal axis. So see, this is normal, this is ray which is coming, and this is normal. So this angle and this angle would be same, and this angle and this angle would be same, so it will be reflected here. So the common point on the principal axis is called focus. Common point on the principal axis, on the principal axis, this point is focus. Okay. Now one more thing to point out here is, if the rays are not paraxial, then the rays will meet, and it will meet in the principal axis only, but at some other point apart from focus. So let me write it. If rays are not paraxial, the point of meeting of reflected rays on principal axis would not be the focal point. Okay. Now we already did this. Let's take a step more and let's see how it works in convex mirror. So in convex mirror, which is also sometimes termed as diverging mirror, and this is of course said as converging mirror, and this is real, and in this imaginary focus we will get. So in this case, let's draw. So this is what I said, and the lens is painted from here. Okay, let's draw a principal axis. Okay, now rays are coming from here. Let's draw the normal. Normal would be what? Normal, as I said, would pass through the center. Similarly, rays coming here, and if we have to draw the normal, it passes through. This is right, and now after this the rays would be deflected somewhere here, but it will appear to meet at the back. Similarly, this will be deflected somewhere here, and it will appear to meet at this point on the principal axis, which is focus. And as you know, this is normal. Okay, and this angle will be equal to this angle, and this angle is equal to this angle, right? This is pole and this is focus, and this is center of curvature, or the line, the rays would come this way, and this way, and it will get deflected here, but it will appear to meet at the point on this lens, which is called as focus. Again, remember that this should be a paraxial, paraxial rays, which means this portion should be very, very small, the aperture. Okay, very good. Okay, now let's find the distance from pole to focus, okay, so let's get started. Distance from pole to focus. Okay, now for this let's draw a diagram, and if we just, so this is principal axis, this is pole as usual. Now the rays are coming from here, right, and then they are getting somewhere here, right? So I can say this, okay. Now let's say this is center of curvature, and this is the normal actually. This is the normal. So this angle and this angle would remain the same, because angle of incidence is equal to angle of reflection. Now let's say this distance is x, and let's say this distance is f. Okay, and this distance is f, right? Now if we just further, now if this angle is theta, and if we draw a perpendicular here which is 90 degree, then this angle will also be theta, correct? This whole distance is r, correct? So let's draw a separate triangle. We can draw triangle like this, and we can draw, this is 90 degree, and this is B, C, this is A, normal, okay, and this point is F, and this is, let's say, small f distance. Okay, now this whole by symmetry I can say is equal, this is r by 2 and this is also r by 2 by symmetry, and let's say this point is B. Now if I draw this figure here, so it becomes what? This angle is theta, this is x, and this is r by 2. Cos theta is equal to r by 2x, or I can say x is equal to r by 2 sec theta, correct? Further, f is nothing but r minus x, so I can say r minus r by 2 sec theta, correct? So I can say f is equal to r minus r by 2 sec theta. Okay, now remember, if the rays are paraxial rays, then theta is very small, correct? So I can say theta is equal to 0 or theta is approximately 0 degree. So sec theta is equal to 1 or f is equal to r by 2. So focus in the case of the focal length in the case of paraxial rays is equal to r by 2, center of curvature, half of center of half of the radius of the center of curvature. Okay. However, so this is in the 95% of your questions, but if we have to calculate it accurately, like from where we got r by 2, this is the calculation. So just go through it, and we will discuss more in the forthcoming lecture.